everyone to my lecture today. And of course, today I'm actually going to be walking you through, what we call the expectation on a finite sample space. Of course, give me 1 second. I'm actually going to project my screen. Okay, so this is a title. Like I said, today the focus is basically going to be on expectation on finite sample spaces. Okay, and you know what? I could remember the other time you've been introduced to sample space. We've talked about experiment. I remember I said experiment is anything at all that generates an outcome. Okay, and of course, the sample space is basically the collection of possible outcome in an experiment. And of course, the sample space can actually be finite and it could be infinite. I could remember yesterday I walked you through the finite sample spaces, and of course, we're still on that. But only that, I remember I said a sample space is said to be finite if there is a limit to the numbers of elements it contains. Okay, this you're actually going to have a countable numbers of elements within a sample space, and of course, that would be called a finite sample space. Okay, and you know what? We have been working on the probability in a finite sample space because if you want to work with probability model, every probability model has sample space. Okay, and you know what? The focus today is basically going to be on expectation. Okay, on the finite sample spaces. Now, the outline today, basically going to talk about indicator function that we also call characteristic function. Then, of course, I'm also going to walk you through the probability as a special case of expectation. Then from there, I'm going to walk you through what we call statistical philosophy. And if we have time, of course, I'm basically going to also walk you through the concept of independence and probably give some examples. Okay, so let's get started with indicator function. Okay, I could remember I've introduced you to different types of function. I think I remember I told you function is a rule, okay, that actually map elements in one particular domain to another codomain. Okay, I remember I gave you different kind of types of functions like the character, I mean the what is it called? Identity function. I remember the constant function. I also walk you through the square function and so on like that. But today we basically want to look at indicator functions. Okay, so we're basically gonna play with some mathematical notations today. If you take a look at this guy now, okay, I'm trying to say we have an event X, okay, which is a subset of sample space. Okay, now having that particular event, what we want to define is an indicator function. Okay, so what indicator function actually means is that it actually map the element in the sample space, okay, into 0 or 1. Okay, so what do we mean by that? Going to 0 or 1? I remember I actually gave an example the other time when I said it's either, a football team or win a championship, or not. Okay, if football team win a championship, we can actually call that one. Okay, if a football team actually lose championship, we actually going to call that zero. Okay, so laterally, so what we actually mean, okay, by indicator function is basically you have a random variable one for indicator function. That is, they're trying to tell you the occurrence of an event. And you have a random variable zero, and that's to tell you, okay, the event does not really occur. So when you take a look at this now, we're basically going to say indicator function equal to 1 if x actually lies in the event. And of course, it's equal to 0. So what this guy actually means is that it lies in probably the complement. Okay, it lies in the complement. Okay, so because when you take a look at this guy here, okay, x difference a actually mean x minus a. Okay, so x minus a, automatically you are referring to the complement, okay, of event a. So by indicator function, actually on the set a, that is what we mean. So we're just trying to say, okay, so it's either the event occur or event does not occur. So this is more of dichotomous in nature, okay, situation where, we got two possible outcome. Okay, and of course, and I said right here, okay, if x, okay, which is a sample space, okay, of a probability model, okay, you remember I told you the other time, every probability model, okay, actually have a sample space. Okay, when the sample space is finite, okay, we have a finite probability model. Okay, if the sample space is infinite, then the corresponding probability model is actually infinite probability model. Okay, now, so that is exactly what I mean. So I'm trying to say now, because we can actually assign the values of 0 or 1, okay, to the indicator, then we can actually call that a random variable where we are actually mapping from, a sample space S to real number. That is what we mean. Okay, so can everyone confirm again if you are hearing me clearly?
Yes.
Yeah.
Okay, thank you so much. Thank you for confirming that. Okay, so that you've been introduced to that. So generally speaking, okay, indicator is a random variable, okay, only that is only assigned the values of 0 or 1. And of course, what 1 means, you can actually picture this, if you're doing business, where in the sample space, it's either there's occurrence of profit or the occurrence of loss. Okay, so when profit occurs, so I'm basically going to say label the indicator function as 1. And when loss occurs, probably I'm going to label that as 0. Okay, so take a look at that. Okay, so that's exactly what we mean by indicator function. Now, I want to go to the second, the objective of the day, where we basically want to show that probability is a special case of expectation. Okay, if the probability is actually, if that PR is a probability measure, then notation for expectation operator is actually E. Okay, now if we basically, we can actually prove that for any event A, the probability associated with the event A is basically the expected value of an indicator. Okay, don't forget I just told you right now, okay, the indicator function, can assume two numbers. It said as 0 or 1. Okay, so if we really want to do this, if we really want to prove that the probability of event A is basically the expectation of, the indicator, we can actually, relate that to, a Bernoulli, okay, Bernoulli, Bernoulli distribution, Bernoulli probability distribution, because, if an indicator is a random variable that can only take 0 or 1, Bernoulli distribution is actually characterized, by two possible events. We use it to model a dichotomous variable, where the random variable can either be 0 or 1. So you remember the other time when I actually said, the probability of that, the f of x for Bernoulli, okay, is basically going to be p raised to power x and 1 minus p raised to power 1 minus x. And of course, the range of fair is basically going to be 0, 1. Okay, now can we have a way? You know what? The Bernoulli probability distribution is a discrete probability distribution. Why discrete? Because the random variable can actually take a whole number. Take a look at that. The random variable x can be 0 or can be 1. Okay, you remember on Monday when I was walking you through all numbers, when I say all numbers start from 0, 1, 2, and so on like that. So right now, okay, what I'm trying to display to you now is what we call the probability mass function for Bernoulli distribution. Okay, so what I'm trying to say, when X follows Bernoulli distribution, okay, where the numbers of time that is repeated is just 1. Okay, the sample size equal to 1, and we basically have a probability p. Now we actually want to show now that the probability of an event is going to be equal to the expected value of an indicator. So how am I going to do that? Then what is the formula? Remember, or the last time I gave you the formula for the expectation when the random variable s is discrete, it is basically summation s f of x. Okay, I'm going to say that again. When the random variable under consideration is discrete, okay, the expectation of x, okay, the expectation of a discrete random variable is basically going to be the sum of x f of x. But you know what? When I'm talking about continuous random variable that we are still going to talk about, the summation we actually change to integral sign. I'm going to say that again. Right now, the expected value of x equal to sum of x, f of x, because of the fact that the nature of the random variable under investigation is discrete, the moment it is continuous, of course, the summation sign is basically going to change to integral sign. Okay, now there's something I'm going to stop my share right now. I want to make use of I'm going to share my whiteboard so you can see how I basically want to prove that. Can you, everyone confirm again? If you can still hear me clearly, are you all still hearing me clearly?
Yes.
Yeah.
Thank you so much. Thank you for confirming that. Okay, I also want to confirm if you are also seeing my whiteboard. Can you see my whiteboard? Okay. Oh, somebody said no. Oh, okay. So you can't see my whiteboard, right? Okay, give me 1 second. I'm basically gonna figure that out now. Okay, so I'm gonna try that again, and I will need you to tell me if you are actually seeing that. Okay, so can you see my whiteboard right now?
Yeah.
Okay, thank you so much. Okay, this is what I'm trying to say. We got a random variable s, okay, that is actually, okay, that can take a value of 0 or 1, and because of that, we said that actually follow Bernoulli distribution. So I'm gonna say when s follow Bernoulli, okay, with parameter 1 and p, okay, the 1 in this case is basically n equal to 1, the sample size, because it's just like the experiment is performed one time, and when experiment is performed one time, it's either you see a success or not. It's just like you have a coin and you toss a coin, and probably you are looking for head. If you flip it one time, it's either you see head or you see tail. Okay, the head that you see, okay, S is going to be 1. The tail that you see, S is going to be 0, because you are actually interested in the numbers of head. Okay, so the f of s, the probability mass function for Bernoulli is actually p raised to power x, okay, 1 minus x, and where your s is actually 0, 1, and what we basically want to do, we want to find the expectation of s. So what do we mean by expectation of x? That's a weighted average. If I have a random variable x that can actually take a different values with a corresponding probability, now the question now is, how do I figure out the mean? How do I figure out the expectation? Okay, like I said, for discrete random variable is basically going to be a summation of x, f of x. The f of x right here is basically going to be a probability distribution of a discrete type. For you to use a summation, the f of s has to be a probability distribution of a discrete type, because we can also have probability distribution of a continuous type. Okay, for continuous type, the summation is basically going to change to integral sign. So right now, okay, don't forget your s is basically going to start from 0. We're going to end up in 1. So right now, so I'm actually going to have s start from 0 to 1 x. What is f of x? Is p raised to power x, 1 minus p raised to power 1 minus x. Take a look at that. Okay, that's exactly what I'm going to have right now. So you know what I'm going to do, that I'm actually going to sum them when s equal to 0, p raised to power 0, 1 minus p raised to power 1 minus 0, plus when s equal to 1, okay, p raised to power 1, 1 minus p raised to power 1 minus 1. Okay, so you can see that now. So I've already applied when s equal to 0, when s equal to 1. Take a look at that. If you take a look at this guy now, because of the fact that you are multiplying the whole thing by 0, this is going to go out. Okay, so what do I actually have now? So I'm going to have p, and this guy here is 1 minus p raised to power 0, right? And then it's raised to power 0 is going to be 1. So now I'm going to have p times 1, that is going to be equal to p. Now, what have we just done now? Oh my God, we have already proved that the expected value of s is equal to p. Take a look at that. So what that means, the probability of an event A, okay, is actually equal to the expected value of an indicator. That's exactly what I've done now, okay, because don't forget your indicator, your x, now it's like a high, is equal to high. Okay, the x is a discrete random variable and can actually take a 0, the values of 0 and 1. So I can say s equal to high. Okay, that's exactly what I mean. So what I've already proved now, so it means I've already proved that the probability of an event A equal to the expected value of that. That's not exactly what I just proved now. And don't forget, I said, okay, the random variable is basically high, okay, because it can actually take 0 or 1. Okay, before I actually clear my whiteboard, is there anyone who want to ask question or who need clarification before I go on? Is there anyone?
What is I?
Yeah, high is an indicator that I just talked about. Indicator that can take 0 or 1. Does that make sense?
Yeah,
What
that's
what the meaning for the BR you write it?
Oh, can you say that again?
What a you write you just erase it, but you write BR that before.
Oh, okay. So let me just maybe this is what I actually, this is what happened. I is basically x, and don't forget x, I can take it as 0 or 1.
No, I mean you write BR and parentheses
Oh,
one.
okay, you mean
One.
I wrote this equal expected value of this. Is that what you mean?
No, you write BR.
I think he's talking about BER and then
Yeah.
1 comma
One
P.
point P, yeah.
I
1 comma
believe
P.
that's the
Oh,
you're
BR.
displaying Bernoulli.
Okay, thank you so much. So you were talking, he was talking about this guy follow BI1P, right? Is that what you mean?
Yeah.
Okay, so this is just to say that a random variable X follows Bernoulli distribution with parameter 1 and P. So what is 1? 1 is just that the numbers of time the experiment is performed is 1. Okay, it's only one time. It's just like you flip a coin one time. Okay, so you're still going to have a situation where we're going to flip the coin so many times, and that is going to be a generalization of Bernoulli. From there, we're going to move to binomial. So right now, so the brand name, every statistical distribution has a brand name. Okay, so what you see now is basically the brand name for Bernoulli. Have I answered your question right now?
Yeah, I just wondering about when we write the BR and when we write the other things like that. So BR means only happened at one, right?
Yeah, BER actually means it's a short name for Bernoulli.
Okay.
Okay, so this is what you mean. Give me 1 second. I'm gonna stop my share now. Okay, now this is what you're trying to tell me. If I want to write Bernoulli distribution, if I want to say a random variable X follow Bernoulli distribution, if I want to write that in a short form, mathematically, I'm going to say X follows Bernoulli. I'm going to use BER, okay? And then I'm going to state the parameters in the Bernoulli distribution. Every probability distribution has a parameter. And for Bernoulli, we have 1 and P, okay? So 1 here actually means sample size. It's like the numbers of trial. Okay, sample size, which actually means numbers of trial, the numbers of time, and P is a probability. Does that make sense to you now?
Yeah.
Okay, so it was just a kind of way to write Bernoulli distribution in a short form. Okay, so I'm going to go back to the lecture material now because we've already achieved. Now, this is what we actually we are trying to say the probability is a special case of expectation, and that is exactly what we just derived. Okay, now the next on the line is philosophy. Okay, what do we want to do here? What do we want to learn here? Okay, we basically want to say, okay, philosophy actually means, we are talking about the love of wisdom. And we basically want to say, what is a perception of philosophers about probability and the expectations that we just talked about. We basically want to know their perceptions. We also want to know the perceptions of mathematicians about what we're doing, about expectations, about probabilities. We also want to know what is the perception of statisticians. When we say expectation, what do we actually mean? And that was why I said philosophers and philosophically inclined mathematicians and scientists have spent centuries, they are trying to figure out, what do we actually understand, what is probability? What is expectation? Do they exist at all? Okay, if they don't exist, why are we actually troubling ourselves doing it? Why are we interested in doing it if they don't exist, if they don't have application? And we actually want to, visit that. Okay, and you know what I'm going to tell you? Because of difference in ideology, okay, according to a philosopher, said no two human beings are genetically the same. I'm going to say that again. A philosopher said, no two human beings are genetically the same. If two human beings are not genetically the same, we're basically going to have different ideology. Okay, we're going to have different belief. And that accounts for the reason why there's a lot of misunderstanding. There's a lot of controversy in this world. We are one philosopher or one scientist, we come against one another because of the fact that they will have difference in ideology. And you know what? what I'm going to walk you through now is that when you ask a question from different philosophers, like I said, about probability and expectation, I know you're basically going to have conflicting opinions because the way it appears to me may not be the way it appears to you. Okay, so that is what we basically want to talk. I think I provided a lot of information here, but I'm basically going to mention two things. Let me tell you this. You know, when we are talking about in statistical analysis, we basically, we believe the fact that we live in a stochastic world. The world is probabilistic. With the, that is our belief. And of course, if we really want to take a decision that we don't want to regret, whether in business, whether in government, whether in medicine and law and so on, like that, we basically need to understand, basic probability or fundamentals. And the reason why we need to understand that is because of the fact that the nature itself is probabilistic in, so now we have, when we're talking about inference, making inference, making judgments, okay, in statistics, okay, we basically have two approaches that we call the frequencies, the frequentism and subjectivism. The frequencies approach, we have the Bayesian, the subjectivism is more or less like a Bayesian approach. And in the modern day world, we also have the formalism. But you know what? I'm basically going to explain to you now. So what we basically, when we're using our frequencies approach, what does that mean? I want to tell you this. With a frequencies approach, we assign statisticians actually that believe in this approach. I'm talking about frequentism. They actually assign probabilities to data. Okay, they assign probability to what? To data. Okay, they assign probability to data. In order for them, they actually want to test hypothesis. I could remember, what you've done before, probably in your lowercase course in statistics, where you you fit a linear regression model, you estimate the parameters of the, the linear regression model from data. Okay, it means you basically want to take a decision on a particular hypothesis, okay, assigning probability to observe data. Okay, we actually assign probability to observe data. And let me tell you this, okay, we believe that when we observe the world, we believe that when we do things several times, that's something that we call in a repeated measure, we basically going to have the understanding of the world. I'm going to say that again. Those who actually subscribe, to frequencies approach actually believe they, performing experiments repeatedly. Okay, when they perform experiment repeatedly, of course, they actually going to understand, the world. But let me tell you this, those who use subjective approach, on the other hand, actually believe that we need what I call a prior information. Okay, we need a prior information because the knowledge on the data set is not enough alone, okay, that we actually need to update our belief. Okay, I'm going to say that again. Somebody like Reverend Thomas Bayes, 1759, actually subscribed to that in addition to the data set that we have, okay, we also need to combine that with a prior information. Oh my God, what do I mean by prior information? The prior information is actually the probability of the state of nature before you collect data at all. I'm going to say that again. Before collection of data, okay, what is the belief that you have? So the Bayesian actually believe that that is very important as well. We actually need to combine that with our data. When you have our data, we're only going to update that belief with the new information, because we basically want to say things could be changing. My belief yesterday may be different from the belief today. You get what I mean? So the Bayesian actually believe that they believe that we don't have probabilities in this world, but we have probability in our mind. I'm going to say that again. The Bayesian believe probability actually don't exist in the world, but they exist in our mind. Okay, that is their belief, that before you actually go into collecting your data set, you have a prior information. And that collecting the data set now will give you an opportunity to update your belief. But the issue with the Bayesian analysis is just that your belief may be different from my belief. There's something that we call the sensitivity of prior. Because of difference in ideologies, we are not likely going to have the same belief. Okay, we are not likely going to have the same belief with different in ideology. And let me tell you this: the formalists, the formalism, okay, when the formalists on the other hand, okay, which actually I'm going to show you now. On the other hand, let me just let me come to, okay, I'm talking about this guy here. The formalism, on the other hand, does not really subscribe to Bayesian notion. Okay, the formalist, on the other hand, does not really believe that there is probability in the mind or probability in the world. They don't even believe in the existence of numbers, but the only thing they know is we only commit ourselves in the world to number theory, okay, or probability theory. That is what they just believe. Okay, we only commit ourselves to that, okay, to the number theory. Now, I think I'm basically gonna, talk more on the frequencies now in terms of notation. For instance, if you take a look at what I have here now, okay, if I have a sequence of x1, x2 up to xn, which are infinite sequence of random variables, okay, and they are defined, for each n. Okay, now I take a sequence of x1 now. Okay, I find the mean. Of course, the mean is going to be x bar, right? I take a sequence of x2. Okay, I find the mean. Then I continue like that until I get to this. I find the average. But you know what? Getting this, before we go into this at all, we actually have expectation. The expectation is this guy here, which we call the expected value of x. What do we mean by expectation? Expectation is more or less like, okay, what do we expect the value to be even before we go into observing data at all? Because a philosopher said, and I quote, our mind cannot be empty. Our minds, okay, cannot be empty. Look at that. There is something in our mind. We always have an expectation before we go into, it's just like a businessman or woman that want to go into business. Before he goes into business at all, what do you think he has in mind? He want to make profits. He doesn't want to make loss. But you know what? There's an expectation, whatever we do, before we even go into it at all, there's going to be expectation. But you know what? The final remain. What happened in reality? Is there a significant difference between what happened in reality and what we expect? And that was why, but there's something we can do is within the statistical framework. Okay, we can actually ensure that what we observe will be very close to what we expect. And that was why when you take a look at what I have here now, I said the x bar get closer and closer to the expectations, but the only condition under that can occur is when we are working with large numbers. large numbers. What do we mean by large numbers? Okay, and that is why I say when n actually goes to infinity, when n is sufficiently large, when the numbers of trials is sufficiently large, okay, we should expect that x bar will actually get closer and closer to the expectation. Okay, now, and that is exactly what I'm trying to say here. Look at that. That is the assertion that the x bar actually get closer and closer to the expectation as n tends to infinity. Okay, and that is actually a theorem, a mathematical probability theory, which we can prove. Okay, I'm actually going to prove that later. Okay, and that's also explain the reason why, we're looking for the population mean. This is a population mean. Okay, this is the average that we're looking for. But we don't have resources to study the entire population. Therefore, we're not going to get mu. But you know what we're going to get? We need to take a sample, right? When we take a sample, we're going to get X bar, which is a sample mean. Now, what can we do to make sure the sample mean actually converge to the population mean? Oh my God, that can occur, when n actually tends to infinity, provided we are working with a very large, sufficient sample, automatically we're going to expect the sample mean to convert to the population mean. Oh my God, the population mean here is basically our expectation. Oh, can you all confirm again if you are still hearing me clearly?
Yes.
Thank you so much. Thank you for confirming that. Now, that is exactly what we need. But let me tell you this. In order to summarize the difference between the frequentism and the subjectivism, which you call the Bayesian approach, I'm going to give you an example right now. Okay, the example I'm actually going to give is this. If I have, I have what is it called? I have a coin in my hand. Okay, I chose a coin. Okay, a coin actually have two sides, right? A fair coin actually has two sides. It's either head or tail. Okay, now when I chose a coin, okay, and I know what has landed, okay, but you don't know it, okay, and I ask you, and I say, okay, can you tell me what is the probability that the coin that I flip right now actually, is head up? Okay, what is it? I'm just trying to ask you now. You don't see it. I've already seen it. Okay, I've already done it. I know what, what has, I mean, I know what comes up. I know, the nature of that, but you don't know it. Maybe I cover that, and I'm not trying to ask you. When I ask you that question, I'm expecting if I the answer that the response I'm going to get, okay, from a frequencies will be different from the one I'm actually going to get from Bayesian. I'm going to say that again. What is the question? The question now is, if I flip a coin, I'm talking about a fair coin, and I'm asking you, what is the probability that head is gonna show up? I already know what shows up, but you don't know it. I cover it. If you are a frequencies, you know what you're going to tell me? You're going to tell me you cannot say you don't know the probability, but the only thing you know, when it shows up head, the probability is going to be 100%. When it shows up tail, the probability is going to be 0%. That is something that is sure to you. But do you know what the Bayesian will say? The response from the Bayesian is going to be, as for me, it is 50%. Okay. But it is whatever, for you, it is whatever you think it is. I'm going to say that again. I'm going to ask the question again. I have a coin, I have a fair coin that have two sides, head and tail. I flip it and I already know what comes up, and I ask you, you don't see it, and I ask you, what is the probability that what comes up is head? Okay, and I said, the frequencies and the Bayesian will have different response. For the frequencies, it's going to tell me, I may not know the probability, but it's going to say there's something that is sure. When it comes out to be head, okay, the probability is 100%. When it comes out to be tail, the probability is 0%. But for the Bayesian, the response you're actually going to get is going to say, as for me, it is 50% that the head will show up. But as for you, it is whatever. The probability is whatever, because why? Because we have different, ideology, a different view. I told you the other time that what distinguishes the Bayesian for the frequencies is the fact that the Bayesian actually believe in a prior information, which is actually the probability of the state of nature before we collect data. When you collect data, they believe that you can update the belief we had before the collection of data. That is exactly, the difference between the two. But if I ask a question, who is right, who is wrong between Bayesian or the frequencies? Oh my God, I'm asking the wrong question, because which one is good, whether Bayesian or the frequencies, it actually depends on whether you want to take action or you want to have an opinion. I'm going to say that again. If you want to take an action, then you go for the frequencies approach. But if you want to have an opinion, okay, then it is basically Bayesian. Okay, in a further course, I know, this is 5101 or 4101. In the 5102 or 4102, you basically gonna, study more about the Bayesian. But you know what we're going to be talking about in this course is basically going to be frequencies approach. And I also want to add this to, I want to say this for the frequencies, we believe that the parameter is fixed. I'm going to say that again. For the frequencies, the parameter is fixed. But to the Bayesian, the parameter is a random variable. I'm going to say that again. For the frequencies, the parameter is fixed. For the Bayesian, the parameter is actually a random variable. Okay, so I'm going to go back to my slide now. So you can actually, okay, somebody said, let me read my chart. Somebody said, so where hypothesis is testing coming from, since we are testing our prior knowledge? Oh my God, that's a very good question. Now, somebody said the hypothesis testing is coming from where?
Okay,
Okay,
so
okay, go ahead.
I was gonna ask, is there any homework this week, Professor? I was like double checking to make sure I could find it.
Yeah, I think I've said that several times, that the first homework will be uploaded on Sunday.
Okay, I
I
just did. I
cannot.
wanted to make sure again.
Oh,
Just-
okay. I don't want to upload homework when I've not taught. I need to teach first.
No,
Okay.
you're just fine. No,
Oh,
I was
okay.
I did that just in case, is like
Oh, okay.
before I go
Okay.
crazy or not. So
Okay.
first
Okay.
assignment's this Sunday coming up.
Yeah, there's no assignment due Sunday because I've not uploaded any assignment. The first assignment will be uploaded on this Sunday, and it should
Okay.
be due the following Sunday, which should be the first assignment of the semester. Does that make
Okay.
sense?
Yeah, I understand. All right. Thank you so
Okay,
much.
you're welcome. Now, somebody in the chat said, so this is where hypothesis testing come from, since we're testing. Okay. Somebody, I think it's not a question. Somebody said, I have a question, Professor. Okay, I just want to ask, the person that said I have a question, Professor, is it the same person that asked about assignment right now, or is it a different person?
Same person. I was just
Oh,
trying to respect
oh,
with the question part.
okay. Thank you so much. Okay, so you can read more about the perceptions, the difference between the frequencies and the Bayesian here. I put a lot of information, for you to be able to grab, but I'm actually gonna move now. Okay, that's a lot of notes. Okay, now this is what concerns us in every else as statisticians. You know, we have already, I told you right now, because the philosophical belief about, you know, the perception of them, about numbers, probability, and the like. But you know what? As statisticians, there is something that we actually believe. Okay, we believe we got two kinds of variables. And of course, you remember on Monday, I actually show you an uppercase S. It's a random variable, you know that? And a lowercase s is actually a realized value. And you know what? Do you know that with basically, you know, a random variable s doesn't have a value yet? Okay, if before you can actually have a value for random variable s, which I'm actually going to have called a lowercase letter, you need to actually perform experiments. And that can only obtain from a random process. Okay, you need to observe something. Okay, that's exactly what we do in statistics. Okay, and that was why I said in everyday philosophy, a random variable s is a mysterious thing. Why? Why is it a mysterious thing? Because we don't have a value for it until you go to the world and observe that. Mathematically, okay, you know, mathematician is going to say, okay, you know, S is just a function on the sample space, which I show you the other time. Okay, but philosophically, they're basically going to say S is a variable and those values depend on the random process. Okay, you know, you need to observe, you need to perform an experiment, you know, repeatedly, you know, before you can actually observe that. That's what we mean. Okay, now I'm actually going to give you this example now. Okay, for any random variable s, the expectation is the best guess as to what the value will be. Let me tell you, before you go to the world to observe anything, you're always going to what you have in our mind, because our mind can never be empty. What we have in our mind is expected value of s. On average, what can it be? Oh, I want to talk about the gas price, right? I want to know the gas price in the United States before I visit the gas stations. What do I expect the gas price to be? That is the expectation of S. And that is the reason why there's a joke. You know, when you say, okay, you know, an average family with a 1.859 children, we're not trying to say they're going to have 1.859 children. Okay, but what we are trying to say, the value 1.859 is very close, you know, to it. And that was why we said, take a look at it. We said it only means that the expected value of s, which is 1.859 in this case, is a number that is close to the observed value of s. We are now trying to say is one of the possibility. Average is not a possibility. The average is just trying to tell us, okay, it is very close to what we anticipate. And the only way we actually going to know whether it is far away or it is very, very close is basically to go for variance. I think I told you the other time, if I really want to know how reliable is my mean. So most all the time we normally want to have an expectation, which is a guess before we even experience the world, before we even observe the world. Our mind can never be empty, but the fact remains after observing the world. Is there a discrepancy between what we observe and what we have in mind? That is another question. Okay. That's another question. Okay, so this is where I'm actually going to stop today. Well, before I go, I want to tell you this, mathematically speaking, if I have a random variable s, that's a discrete random variable, where the sample space actually exists. Of course, the probability math function is f of s, and if I want to find the mean, which is the expected value of s, is this. That was the formula that I used the other time. Okay, so the other material I'm actually going to continue on Monday. For that, before I go today, is there any question? If there's anyone who need
How does it work?
clarification?
I think there's like a lab section tomorrow. Is that going to be the same link?
Oh, um, this is this is 4101 and 5101. You are asking about lab session, right?
Yeah, I think
Hello?
there's a lecture tomorrow, right? But it's not a lecture, it's supposed to be a lab session.
Yeah, so that would be the information about the lab session tomorrow. I needed to check the syllabus. My TA will be the one that's actually going to conduct that. So, but you know what? If you look at the syllabus and they don't, in fact, what I'm going to do, I'm also going to send and I'm going to make an announcement about what the link, the Zoom link you're going to use for tomorrow's lab. Okay,
Okay, thank you.
you're welcome.
Whether we need to download the R Studio before the lab section.
Okay, if you're talking about 4101 or 5101, lab software is not compulsory. Does that make
Okay.
sense?
Yeah.
It is only compulsory for my other course, 3032. But 5101, 4101, the software is the use of software is not compulsory. And I know what my TA is actually going to walk you through. It's basically going to be like something theoretical and even something software, but it is not compulsory, but only that you are just encouraged, for additional information. Does that make sense to you now?
So the lab section is more like the practice and the review section, right?
Exactly.
Okay, got you. Thank
Yeah.
you.
You're welcome. Okay. I want to thank every one of you, for attending my lecture today. Like I said, the first assignment will be released on Sunday. Now, now that we've done something now, then assignment, I can, actually give assignment, which should be uploaded on Sunday, and it's basically going to be due on Sunday. But you know what? When assignment is uploaded, you're basically going to receive the notification on Canvas, and you are expected to submit the assignment through Canvas. There's going to be a port. There's going to be an assignment one port that will be created. Okay, I want to appreciate every one of you today, for attending my lectures. I hope you're enjoying it until on Monday that I'm actually going to come your way again. Make sure you stay safe and have a lovely weekend. Oh my God. Bye for now, everyone. Yeah.
Thank you.
You're
Have a good
welcome.
weekend, Professor.
Thank you.
And you too. Thank you too. Thank you.
Hi, Professor. I have a question.
Okay, go ahead.
Where can we find the information about the lab section?
Okay. You know what I'm gonna do? The information about lab session will be fine on the syllabus, but you know what I'm gonna do? Today I'm also gonna send the detailed information through the announcement section for everyone to see.
Oh, okay. Is that the same time with today's lecture or?
It's not going to be the same time because it is my TA that set. I'm going to check out because the